Hello everyone, thanks for watching this video. Today I am going to talk about our work about using unreliable pseudo-labels, which is an effective pipeline to make sufficient use of unlabeled data in semi-supervised semantic segmentation. Semantic segmentation, as a fundamental task in computer vision field, relies on large-scale annotated data. To alleviate this problem, many attempts have been made toward semi-supervised semantic segmentation, which learns a model with only a few labeled samples and numerous unlabeled ones. A typical solution is to assign pseudo-labels to the pixels without annotations. Concretely, given an unlabeled image, prior arts borrow predictions from the model trained on labeled data, and use the pixel-wise prediction as the ground truth to in turn boost the supervised model. However, model may suffer from incorrect pseudo-labels. Existing approaches propose to filter the predictions with their confidence scores. In other words, only the highly confident predictions are used as the pseudo-labels, while the ambiguous ones are discarded. However, one potential problem caused by only using reliable predictions is that some pixels may never be learned in the entire training process. For example, if the model cannot satisfyingly predict some certain class, example, chair in this figure, it becomes difficult to assign accurate pseudo-labels to the pixels regarding such a class, which may lead to insufficient and categorically imbalanced training. From this perspective, we argue that, to make full use of the unlabeled data, every pixel should be properly utilized. As discussed above, directly using the unreliable predictions as the pseudo-labels will cause the performance degradation. In our paper, we propose an alternative way of using unreliable pseudo-labels. We call our framework as U2PL. First, we observe that an unreliable prediction usually gets confused among only a few classes instead of all classes. Taking this figure as an instance, the pixel with white cross receives similar probabilities on class motorbike and person, but the model is pretty sure about this pixel not belonging to class car and train. Based on this observation, we reconsider the confusing pixels as the negative samples to those unlikely categories. Specifically, after getting the prediction from an unlabeled image, we employ the per pixel entropy as the metric, see this figure, to separate all pixels into two groups, i.e., a reliable one and an unreliable one. Our pipeline contains a student network and a teacher network, where the teacher is momentum updated with the student. Labeled data is directly fed into the student network for supervised training. Given an unlabeled image, we first use the teacher model to make a prediction, and then separate the pixels into reliable ones and unreliable ones based on their entropy. Such a process is formulated as this equation. The reliable predictions are directly used as the pseudo-labels to advise the student, while each unreliable prediction is pushed into a category-wise memory bank. Pixels in each memory bank are regarded as the negative samples to the corresponding class following these rules. To avoid all negative pseudo-labels only coming from a subset of categories, we employ a queue for each category. Such a design ensures that the number of negative samples for each class is balanced. This figure gives a visualization of the feature spaces learned by our method and its supervised counterpart. Experimental results on various benchmarks and training settings demonstrate the superiority of our approach over the state-of-the-art alternatives. These are qualitative results on Pascal VOC 2012 dataset. From left to right are input images, hand-annotated labels for the corresponding image, only labeled images which are used for training without any unlabeled data, the vanilla contrastive learning framework, where all pixels are used as negative samples without entropy filtering, and finally predictions from our U2PL. Yellow rectangles highlight the promotion of segmentation results by adequately using unreliable pseudo-labels. These are qualitative results on the Cityscapes dataset, which also demonstrates our superiority. Finally, thanks for listening. You can refer to our paper for more details.